our next speaker is Matthew McIlree, who will tell us more about constraint programming and some interesting proof logging techniques and propagation algorithms. Please, Matthew.
Yeah, I don't have enough space for the words hopefully interesting, but we'll see how we get on. This is going to be somewhat a continuation of the talk that you've just heard. I'm going to give you kind of a very high level look at some of the constraints that I've done so far in my PhD. I'll try not to get bogged down too much in details, but I'll more give you a sort of big picture idea of the sorts of things that we can do. I'm in a nice position in this talk, talking at this point, because normally I have to spend quite a bit of time explaining the background, but what I'll do instead is I'll put a list of things up here that I'm assuming everyone is happy with now. And if not, I can give a 10-second recap. So proof logging is a useful thing. The VeriPB proof system has a set of rules. The one that I maybe used that maybe worth recapping again is RUP, but we can get to that when that comes. That we can natively reify PB constraints within the proof system. The basic idea of constraint programming, so we have search and we have propagation, and we have many different propagation algorithms. And that generally speaking, we can encode CP problems to PB problems for the purposes of proof logging. And then finally, the general requirements of what we need for proof logging for CP. That being, we output a RUP statement every time we backtrack, and then propagators log their justifications. All of this generally okay at this point? Okay, I'm seeing no objections, so I shall move on. So the main challenge that gives me something to do for the next 4 years is that there are a lot of propagation algorithms in the world of CP. And I've been told I don't get to graduate until every single one of them has proof logging and is implemented in the Glasgow constraint solver. Maybe steps on the road to that is to say, let's look at some propagation algorithms that perhaps give us other constraints, so they're more fundamental in that we can encode other constraints in the form of these propagation algorithms, or maybe that are somewhat unusual in the way that they're propagated, or at least have kind of interesting, non-trivial propagation algorithms. The other thing, I'm going to tell you about 3 constraints today that these 3 have in common, is they might have been ones previously when Kieran stood up and claimed that we will soon be able to do proof logging for all of CP, that someone in the audience might go, well, it's all very well that you can maybe do linear inequalities or perhaps even all different, but you'll never be able to do regular language membership because this is just so far from pseudo-Boolean lands that it's just, there is no hope. So I'm going to try and refute that in a sense and say that actually there's nothing particularly special about these constraints, despite their inherent weirdness on the surface, that means we can't proof log them. So this talk is a bit of a mashup between the talk I gave at CP last year, which was on, I kind of artificially put smart table and regular together as smart extensional constraints for the purposes of one paper. And then next week at CPIOR, I will be presenting the circuit constraint and proof logging for that. And that's slightly different because of the kind of consistency that enforces. So basically, we'll just do these one by one. I will tell you what the constraint enforces. I will tell you how we can write down a hopefully fairly obvious pseudo-Boolean encoding of the constraint. And then I will give you a high-level picture of what the generally accepted constraint propagators do and how we can proof log them. So without further ado, we shall start with the smart table constraint. So Kieran mentioned in the previous talk the idea of table constraints. And these are in some sense the most general, maybe fundamental view of constraints or constraint programming constraints. Basically, we have a set of finite domain variables. And for the regular, I shouldn't say regular, not be confusing, for the normal table constraints, we would just list the tuples of allowed values. And this could be a very long list potentially for this set of variables. And this actually admits some very efficient propagation if we're able to do this. The problem being that for certain kinds of constraints, if we were to enumerate all the solutions, we might get an exponential table constraint in size, which is not going to be efficient proof log. So as you can maybe see from this picture here, The idea with smart table constraints is to try and get somewhat a happy medium between listing all of the tuples out fully in extension and having a more compact representation. So what we do is we allow the entries of the tuple to be a restricted set of very small binary or unary constraints. So before in the table constraint, we might have had 1, 2, 3, 2, 2, 1 here. Instead, we say, okay, one of these two rows in the tuples are the only things that are allowed to hold. So either the set of three constraints, x is less than y is in the domain 1, 2, or z is equal to 3, either those things hold, or x is not 1, y is equal to x, and z is less than y. And that characterizes all the possible solutions to this smart table constraint.
And we allow them to overlap different rows.
So they can overlap. The restriction is that within each tuple, you're not allowed to introduce a cyclic dependency between the variables. So we couldn't have x is less than y is less than z, and then z is less than x, for example. So the tuples themselves can overlap. Within the tuples, we can have some amount of overlap as long as it's not a cyclic overlap. That is a restriction kind of artificially introduced for the purpose of having efficient propagation. But for encoding constraints that we might want to encode as smart table constraints, that's the only restriction we really need. I guess if you're more familiar in SAT, you could think of this as a kind of disjunctive normal form as opposed to a conjunctive normal form, because we're saying either this or this, but within each tuple, all of them must hold. So we can encode this very straightforwardly in pseudoboolean land, providing we know how to encode all of these simple constraint entries. So what we'll do is we'll introduce a reified variable. Oh, I should say for this, we're going to assume the variables are in the domain 1, 2, 3. So very tiny domain. And that we would encode this using either the two's complement or binary encoding, as Kieran talked about previous talk. So what we'll do is we'll encode each entry constraint using the simple, straightforward PB encoding that we should hopefully already know about. So for example, x is less than y would be encoded just by taking the linear inequality over those bits. And then we double reify that on this selector variable, which I'm going to call E with a subscript for entry. And remember that these reified constraints are just syntactic sugar for two native pseudoboolean constraints, but I'm going to hide them themselves in there. So we will first go through all of the entries and reify them against their own tuple selector. And then at the end of that, we can create pseudoboolean constraints that encode the meaning of the tuple. So S1 is now saying the first tuple holds, and that means the three entry constraints have to hold. And then S2 means the second tuple holds, and that means those corresponding three entry constraints have to hold. And then finally, there's disjunctive normal form, part of it saying, okay, we must have either S1 or S2. So it's not too surprising that we can write this down in a fairly coherent way. And this is one of these encodings where we're going to stand and say, hopefully this encoding is obviously enough the exact semantics of this smart table constraint that you're not going to worry that we don't have a formally verified encoder yet. But maybe you can disagree with that and that you would maybe be entitled to do that. But we're going to say this is an obvious enough encoding. So I will put in this talk encodings at the top of my little proof scroll with a gray box around them. So just know that's not part of the proof, that's the PB model that we're referring to. So we can efficiently propagate smart table constraints in the similar way that we can efficiently propagate table constraints. So the idea is we want to collect for a given point in the search tree all of the values that are supported by either tuple. And then we want to find values for any of the variables that are not supported, so not in either of those lists of values, and then we can remove them. And the way we do that is we think for a moment and realize that each of these tuples, because it's a conjunction of small constraints, is really its own small little sub CSP in itself. And so we can actually filter that as a CSP. And because I required that it was acyclic, we can get what you call global consistency on these small constraint satisfaction problems. That is, every value that is not supported across all three constraints is removed. So we'll actually write the tuples as their little trees. So this is the site. So we have a tree for x and y, and then z is on its own. And then on the bottom tuple, we have X, Y, and Z. And then we're going to filter all the subtrees in each tuple one by one. And that's by a 2 pass over the trees. So the filtering will go as follows. And what I'm going to do is I will show you, rather than telling you in general how to proof log this, I'm going to show you what the solver actually outputs in the proof log, and then hopefully the general idea will be relatively clear. So what we're going to do is, as we do filtering over the trees to collect supported values, we're going to output those filtering inferences, logging them by RUP as we would if we were solving these small CSPs normally, except we're going to make them conditional on the tuple selector, so on these S1 or S2 values. So first of all, if the domains are 1, 2, 3, we would start by filtering this constraint, and we know that X is less than Y, so Y cannot be 1, because then there's no smaller value for X to take. And so as we're collecting that inference, we will also proof log it. We will output a RUP step that says S1 implies that Y is not 1. And then we filter our next constraint, and this says Y is in the set 1, 2. So in particular, Y cannot be 3. And because this is a 2 pass to get the full supports for this tree, we then filter the first constraint again. And because we've concluded that Y is not 1 and not 3, we know Y is 2, and X is less than Y, therefore Y is 1. And again, we can log this by RUP. And the reason these all follow by RUP is because these PB constraints are all single. So like Kieran was saying before, effectively, these filtering inferences are just one step of look ahead. So when we take the negation of these implications, we get S1 will propagate this folding, and then X1, or whichever one of these inferences on the right-hand side, will immediately contradict the entries. So we continue to do that, and we will output the inferences for the bottom filtering as well. And so our solver has now collected all of the values for each tuple that are supported. And it's going to see that between these two, now which is the value again, I try to remember, I think it's that Y cannot be 3 in either of these. Well, no, Y cannot be 1 in either of these, correct, because X is not 1 and Y is equal to X, so Y is not 1 here, and we knew at the start that Y is not 1 because it's greater than X. Yes, and that's not possible. Okay, so we log that in either tuple, and that means that the smart table propagator can say, okay, overall now, we can remove 1 from the domain of Y. And because we're logging things as we go along here, and we have this S1 and S2 is greater than 1, we can now disrupt our inference. And that's all we need to do. So the smart table constraint on the surface looks like a really complicated thing with lots of little sub-constraints and stuff. In a sense, was really easy. And in fact, we were able to do this only using RUP. Now, what I've written here is some justifications that look like propagations that would maybe take place at the very start of search. So before we said that our justifications have to be the sequence of guesses that we've made implies the propagations that we get. So if we were deeper into search, this would be some long sequence of guesses implies Y is equal to 1. Now, when we demonstrate this proof procedure in our paper last year, we omitted all of these guesses on the left-hand side to show the general idea. And we found actually, as we think about it a little more, that we're kind of relying on an implicit theorem to get this result that I'm actually going to share here, just because although it's quite obvious at one level that this is true, maybe if you're proof logging, you might be relying on this as well. So this is how we've written it up formally, and this is in an appendix to a currently unpublished paper, so it's a bit hidden. But if we have a PB formula F and a partial assignment, and we apply that partial assignment to the formula, and then from that restricted formula, we derive a constraint using a cutting planes and RUP derivation of some length, then we know an efficient way now to derive from the original formula, so from the unrestricted formula, a reified version of that constraint that we derived. And that reified version is all of the literals that encode the partial assignment that we used for the restriction implies this constraint that we derived using our previous procedure. So this is, I came up with this to try and state this in the sort of most general way. The way we kind of use this in practice is we might exhibit some proof procedure, right? And say, I've just made up random PB constraints here, but I'm saying we've derived these three things, and then we know, because we can derive these three things in this way, that if we were reifying them all in some literals that led the variables to be set in the way that they are, then that's fine. We can just stick a reification on the side of our entire cutting planes proof, and it all still kind of works. And the intuition for why that's true is you basically just reuse the same proof with reifications on either side, except you might need to do some literal axioms to fix the reification coefficient at various points. So maybe that's super obvious, maybe it's not. I thought it'd be a good thing to put in at this point, because now you can say, okay, this is a complete proof procedure for smart table. We can do all of that under a sequence of guesses as well. And actually it's going to come in useful later as well. So that's all I've got to say about smart table constraints. Before I move on, I guess questions? Cool, that's fine. So now taking the idea of listing explicitly all of the solutions to a constraint sort of even further and taking even more of a step back, what if we were to say, for a sequence of variables, the values taken by those variables as a sequence must be recognized by some regular language deterministic finite automaton. So that could be a regular expression, but for the purposes of this constraint, it's going to say you provide the constraint as like part of the definition of the constraint in your solver, a set of states, a set of transitions, the starting state and the final states, and that's going to give you an automata that recognizes some regular language. And then you tell it, okay, here's a list of variables. The values taken by those variables must be recognized by that DFA. So that's a really fun constraint because it allows you to encode all kinds of arbitrary things in a very sort of compact way. So Kieran mentioned before the European Working Time Directive. I'd be interested to know whether that's a regular expression, but certainly for kind of awkward shift scheduling constraints, it turns out that you can basically compactly refer to this as an automaton and treat it as a constraint. So we know the drill by now. We have this constraint. We want to express it in pseudo-Boolean form so we can add it to our proof logging CP solver. So what are we going to do? We are going to, and this is a common theme, we're going to use variables that exist only in the proof. So last time we had E variables. I've changed this from the last time I gave this talk. So I'm now going to say S variables, which I maybe should have called Q variables. I was kind of struggling to decide on what the clearest letter, but if you think S for state, so SI means the state after processing I variables in the regular expression. And this is going to be something that exists only in the PB world. But if we define that, we know that the initial state, so S0 will be 0. And we know we have to end in a final state. But for this particular example, we'd add to the PB model that S5 is 3 or S5 is 4. Those are the only two places that we can end if we can hope to satisfy the regular language membership constraint. And now we need to encode all of our transitions. So for each xi and j in the domain of xi and every state, so this is basically every possible configuration that we can be in at any point, we're going to put in this PB constraint, which looks very similar to the dynamic programming knapsack state transitions, although it's a bit simpler that Kieran showed you before. But basically saying xi equals j and si equals q implies that the next state, so the state after processing I plus 1 variables, is going to be whatever the DFA tells you it ought to be. And that includes, now in this, I've not included not allowed transitions. So for example, from here, there's no 1, so we're just assuming that's a disallowed transition. So the PB constraint would be this implies false instead. I maybe should have written that to make it explicit. But we basically just list our transition table in the PB model. So again, I'm going to argue that this is a simple enough encoding that we can just trust it. And again, you might disagree, but hopefully it's relatively clear. And the nice thing about this is, again, this is a relatively propagating encoding for the regular constraint. Now, there was a fully propagating SAT encoding for the regular constraint given by, I think, Bacchus, which we could have used, and that might have made proof logging simpler. But it's kind of this trade-off between do we want to put all of our logic into the encoding? So to make the proof so short, but then we're left with this kind of nasty, well, I don't really trust now, you've just shifted the trust to the encodings. Instead, we're using a simpler encoding and we'll put more logic in the proof. And hopefully that design decision seems reasonable. So how do we propagate the regular language membership constraint? Again, there is an efficient algorithm for removing all inconsistent values from domains. So when I say that, I'm meaning in CP terms something called domain consistency or generalized arc consistency. And this is kind of like the most amount of pruning that you can hope to get out of any single constraint. So what the propagator does is, rather than storing the DFA just as it is, it uses a bit of state that stores a kind of expanded version of this. So it has a layered directed multigraph of all of the states after each point of the variable. So you can think of a transition between layers as being what value the variable takes at this point. And the allowed transitions between layers are specified exactly by the allowed transitions in the original DFA. So to start with, we will have a whole bunch of things. This is exactly the same DFA if you like turned on its side and then shook out like a concertina. And what the regular constraint will do is it will notice that any valid assignment to the variables is only possible if it's part of a path that goes from Q00, our start state, all the way to one of these end states. So consistency for the regular constraint is about removing any of these edges between layers that are disallowed, that are not part of such a path. And we can really efficiently compute this by just going forward across this and then back again. So we start in the start state and we see what we reach in the second layer and we remove everything that doesn't come from something other than Q0. Then we have reached two vertices, so we can remove everything that comes out of vertices that we didn't reach. And then we can take another step along and remove more things, and another step along and remove more things, and continue until we get to the end. And then once we've got to the end, we might have reached several vertices. So we've reached 1, 2, 3, and 4 in the end here. But we know that the only valid paths are the ones that end in state 3 or 4. That's why they've got the thicker ring on them. Those are the accepting states. So we can remove anything that goes to something that's not an accepting state. And now we'll notice we're nearly consistent, but we now need to continue to check backwards that there's not any dead-end vertices that don't go any further. So we can continue to prune. And now we're left with this really nice thing that you might recognize if you're into decision diagrams. This is effectively a decision diagram representation of the regular constraint. So we've just pruned all of these disallowed values. And then all the propagator needs to do at this point is keep this graph state at maybe in some efficient representation and keep it up to date. So as variables are removed from domains, it just needs to reestablish consistency by a forwards and backwards pass on the graph. So I do proof log all of these initial removals and all of the backwards removals, but I'll just show you the proof logging that needs to be done for a single. So we're going to trigger the updating of a regular constraint by removing a certain value from a variable's domain. And I'll show you how to proof log that. And then I'll tell you that we can proof log the initial forwards and backwards pass in exactly the same way. So suppose that x3 is not equal to 1. I'm going to guess that's what I put. And you won't know if that's true because you won't remember probably that, okay, blue was 1, red was 0, and 2 was yellow. I should add a wee key there to remind you, but that's fine. So x3 is not 1, so the blue vertices disappear between the third and the fourth layers. And now the graph is in an inconsistent state. So we need to do some bookkeeping, as Jakob called it, to add some things to our PB model to make sure that if we remove any values due to the regular constraint in future, that everything's going to propagate nicely. So we'll start with our backwards pass. So from the point of the removal, we have one dangling vertex that doesn't have anywhere that it can go. So that should disappear. And in the proof log, we want to also add this edge removal to keep the proof up to date. Now, if you think about what an edge basically is in the pseudo-Boolean world, it's not just a state variable, and it's not just the value that an x variable takes, because there can be multiple edges coming out of each state, and there also, for any given layer transition, there can be multiple, so there's 2 red arrows here. So we actually need to disallow the conjunction of the 2 things. So we would wrap not S2 is 1, so not this state, and not x2 equals 1. So not from this state, no red. And that disallows exactly this edge. And this differentiates it from decision diagrams a little bit because we could have multiple layer crossings in that case. And this is very nice because this is just rough. Yeah.
Do you want to disallow the edge here, or do you want to disallow the node here, the Q31?
So
because if there are multiple edges, basically you want to say, well, I cannot leave Q31 anymore, so just throw it out.
Yeah, there's actually no particular difference in this case between, like, I could actually just log Q31 is not allowed in this case because it's all gone.
But is there any case where you would want to disallow an edge, but not disallow either the starting node or the target node of that edge?
I'm going to be honest, I can't remember. It's quite possible that no, you don't.
At least the cost regular, you'd probably want the edges.
Yeah, I mean, well, I'm just going. So I did this a year ago, and I roughed a lot of things back then. And actually, just even as I was going back over these slides, I discovered the proofs I'm generating are pretty like overly cautious in what they're writing down. So like I will, like for smart table, for example, I kind of only realized literally just as I was making these slides, a way to make the proofs a whole lot faster, which would be that rather than outputting everything really neurotically as soon as you find it, you could actually hold on to the PB things that you're going to output within the solver and only output the one that you know you're actually going to remove. But I guess the philosophy that was given to me at this point was, don't worry about writing the best proof logging, just get one that definitely works. So in this case, this is definitely going to be RUP because the negation of this is going to be x2 equals 1 and x2 equals 1. And then because the left-hand side of that is now gone, then this is certainly not going to be able to hold, and that's going to propagate. So the reason the backwards pass propagates so easily is because these implications go from left to right. That's the kind of the intuition for that. So we can remove, and if there were more things to remove in the backwards pass, we could remove them in exactly the same way. The forwards pass is a little bit trickier. So from here, we want to remove this variable because it's got no incoming edges. We would like to just do the exact same thing and just drop this node out of existence. That unfortunately, I don't think in this case, I think in this case it's fine, but I was able to find cases where this does not unit propagate, and we need to be a bit more careful to make sure that everything's going to propagate. So what we do is we first disallow every previous node combination for the third and fourth layers. So we say, and again, this is possibly a little bit overcautious because clearly Q3 is going nowhere. But we RUP that for any of these nodes, we're not going to reach Q42 from them. And because this gives you 2 states in this eliminates 2 of these, which gives you better propagation. Again, that's more of an intuition than a formal argument. But essentially, as long as we log all those things, so that's just essentially one extra layer of logging, then we can log our edge removal. So this is a whole lot of bookkeeping to say that once we're now back in a consistent state, the proof log will have been updated so that all of the edges and corresponding nodes will be removed by unit propagation. So that when the regular constraint is able to infer something, in this case, I'm not sure it is, but that would just follow immediately by unit propagation. So that was.
Do you have a constraint saying somewhere that at least one of the S3 guys should be true?
Yes,
okay.
Precisely.
So,
yeah.
So you're also encoding that on top, that at every step, you pass through every layer, basically.
Yeah.
Okay.
Yeah. So the SI, when I say we're going to introduce a variable in the proof, I'm kind of sweeping under the rug 2 choices, which is that we're going to encode, even though this doesn't exist in the CP world, we're going to encode this extra variable anyway. And we could, so I think for this constraint implementation, I went for was actually a direct encoding of the SI variables. So all of these are, yes, they're just single variables, and then they have an at least and at most one, no, they have an at most one constraint on them. We could also have used these as a binary encoded version of these S variables if we wanted to, and then we'd need to reify each of these like flags onto that binary encoding as well.
You could also have derived it inside the proof, because you know that you need to end up on the right. So you didn't need to assume it in the OPP file that you have, but you go through all the layers probably. Because you need to start on the left and you need to. I guess you could get it there.
You can get it. We do derive it from knapsack,
Yeah.
but it's morally, I think it's okay to put this in the OPB file.
Again, it's like it's a trade-off. Like we can put as little as possible. Like Peter, when I did this talk at CP last year, and I showed the smart table, Peter Stuckey immediately went, well, you don't need to reify both ways. The semantics of the constraint are still true. And it makes life just that little bit easier without sacrificing too much in terms of the encoding being understandable. What is the counter argument to that? But if we want to be like super purist, we could say, no, we want the absolute bare bones like that is necessary in the PB model. And then everything must be introduced on the fly in the proof itself for like true enlightenment. But that's a question to be had. I will be going back over these constraints in due course, because we've actually learned a lot more about this now that we've done knapsack and decision diagrams, because it turns out that this whole procedure is kind of like a special case of what you do for proof logging for dynamic programming, or as the paper is now called, proof logging for things involving states and transitions, as in dynamic programming and decision diagrams. Okay, any question? Well, we've had some questions, but any further questions about those two constraints before I move on? And how am I doing for time?
15 minutes to go at least. You started a bit late also. Depends on how much coffee we want during the break.
Yeah. Well, I was worried coffee might be brought at 3 o'clock and then everyone would just disappear. But that's okay. I don't think circuit constraint can beat coffee, but that's fine. So one final constraint to talk about, and this is completely different from those previous two. So we're taking a full step away from smart extensional constraints now. And the reason that this one is interesting is the two algorithms that I gave you before both enforced domain consistency, so full consistency. The circuit constraint has no such hope, and I will show you why. But first of all, I'll explain what the circuit constraint is. So forget circuits in the terms of logical circuits. We're thinking circuits in terms of Hamiltonian circuits. So basically, it uses a successor representation to treat treat the values of variables as being vertices in a directed graph. So say we had 5 variables and 5 values, then conceptually we have a graph with, that's 6, 0 to 5, 6 vertices. And we view there being an edge in the graph specifically if, so the edge between vertices I and j exists when xi equals j. So this is the successor representation. And then the circuit constraint says when you view the values of the variables like this, the edges that they form must form a Hamiltonian path, Hamiltonian cycle of the underlying graph. This is useful for many things, for vehicle routing, for graph problems, for traveling salesman type problems. In terms of CP, the circuit constraint is kind of viewed basically as being 2 constraints rolled into one. So clearly we have an all different on the constraints here because the values of the variables are effectively just a permutation of the indices of those variables. If all we force is all different, we can get situations like this that are not Hamiltonian cycles. We have subcycles. So we need to add, and the CP propagator views this as a kind of separate task. So we know how to enforce all different. We're now going to enforce a propagator that says, and these subcycles are not allowed. And this has been called various things in the literature: subtour elimination, subcycle elimination, no cycle constraints. These are very well-known things. And once we enforce that, we will get a Hamiltonian circuit. Now, Kieran flashed up very briefly how to do all different. And there's already been a paper on how to do proof logging for all different. So I'm going to essentially ignore that and say, we know how to do that. We know how to encode all different. We know how to justify it. Let's think about how to justify and encode the no cycle part of the circuit constraints. A brief word about consistency for circuit. I said there was no hope of getting full domain consistency. So in an ideal world, we'd have some set of values for each of the variables, a certain domain, and these would correspond to possible edges in our underlying circuit graph. And so to get full domain consistency, we would have to remove any edge that is not possibly part of any Hamiltonian circuit. And if you think about that for a minute, you realize that, well, then we'd have to remove all the edges in the case there are no Hamiltonian circuit. And if there was a polynomial algorithm for that, there'd be a polynomial algorithm that detects whether there's a Hamiltonian cyclogram, which we know we cannot do. So we are not all lost in terms of hope, because we can still enforce partial consistency efficiently in CP world. And in fact, this is what solvers do. There's not actually a huge amount written up about this in the solver literature. It's kind of mentioned as folklore. I remember following a chain of references back only to get personal communication at a certain point, which is always great fun. But luckily, it's documented somewhat in everyone's codes where you can see what most of the solvers are doing. And so what I did is try to collect together a lot of the ad hoc propagation algorithms that are used and then see how easy it would be to proof log most of them. And we got a kind of nice result out of it, which is that we came up with one proof logging procedure for doing one thing and then discovered that you can actually basically just reapply it for like a whole ton of different pruning inferences that the algorithms were doing. And so we make the claim, or I'm going to make the claim next week, that we can basically do all of circuit propagation and proof log it relatively efficiently. So we need the PB encoding for our subcycle elimination, assuming we've got a PB encoding for all different already. And so what we're going to do, again, is a bit like Groundhog Day, we're going to introduce variables that only exist in the proof. Once again, these could be direct encoded or 2's complement encoded. For this particular implementation, I used 2's complement. And we're going to say that PI is the, I struggle to find the best way to phrase this. I'm calling it P for position. So the position of vertex I relative to the vertex 0. So that's like the number of steps in the final Hamiltonian circuit away from 0 PI is. So here P0 is 0. And then because this is a full solution, P5 is then 1, P1 is 2, P2 is 3, and so on. That's how the P variables get set. So we want to encode those semantics for the P variables into our PB model. And basically, if we have these variables and they need to all be set, we know we can't possibly have a subtour because otherwise there's no way to consistently set them all starting from 0. So for each xi, each j in the domain of xi, where j is not 0, so where we're not at the very end of the circuit, when treating the start of the circuit as being 0, we will say that xi equals j if pj, no, sorry, we'll say that if xi equals j, pj will be exactly 1 more than pi. So this is the successor relationship for the position variables.
So xi equals j is like from vertex I, j is
Yes.
the next guy I go to.
Yes, so if x2 is equal to 3, then p3 is 1 more than p2, and we see that's true. If x0 equals 5, p5 is 1 more than p0. So that's the setting of the p variables. And this encoding actually, and this is out of the 3 that I've given you so far, probably the one that's stretching the, this is clearly Hamiltonian circuit the most. But I'm still going to argue that out of all the circuit encodings that exist, and obviously ILP people solve traveling salesman problems all the time, and they do all sorts of crazy things for encoding circuit constraints, I'm still going to argue that this is one of the simplest, and we did not pick this because it's got good propagation or it's useful for solving. It really is pretty straightforward to see, as long as you don't get confused, as our reviewers did, about what the p variables are meant to represent. So there's our encoding, and now I'm going to tell you about some of the propagation algorithms, and I'm going to get increasingly more abstract about this because we don't want to get bogged down in detail. So the first propagation algorithm keeps track of what we'll call chains of vertices. So basically, only thinking about the variables that are currently assigned, I'm going to show with the thick blue arrow, and not the variables that are still have possible values in their domain. If there's a chain of such vertices, then we can infer, because we know there's no subcycles, that the end vertex of the chain is not equal to the start vertex of the chain. Because that's like doing one step a look ahead and saying, well, if I assign this, then I would have a subcycle, but it's not allowed. So that's fine. So we would remove that. How would we proof log this? It's not going to be rough because there's clearly going to be no propagation of our p variables whatsoever just from setting these, because we need p0 equals 0 even just to get us started. But what we can do is we can do a very simple cutting planes argument. So we will have these constraints from the encoding. This is just instantiating these with the particular p-values that we have for these three vertices. So x2 equals 3 implies p3 is p2 plus 1, and so on. And then we just add all of these up. And what's very nice is because these form a subcycle of the p variables, everything is going to telescope and cancel out. And so what we're going to get left with is the things on the left-hand side of this reification is going to imply all of this is equal to something that's not true, because everything's cancelled out on the left-hand side, and we're left with a non-zero number on the right-hand side. And saying that these three variables can't all be true at once is exactly the same as saying that x2 equals 3 and x3 equals 4 implies x4 is not equal to 2, which is exactly the form of the justifications that we want to produce for CP. So that's very nice. And we can also do that for an even simpler propagator that I'm not bothering to mention, which is just if there is a subcycle contradict, which is kind of like the bare minimum that you absolutely need. So this is called, in some bits of literature, the check and prevent algorithms for circuit propagation. And actually some CP solvers only implement this, and that's actually good enough for the benchmarks that they're looking at. But we don't want to tell people what propagators they ought to use. Yes?
You probably said this already, but the PI variables, I should think of them as just bit strings, which are interpreted as integers by this exponential sum.
Yeah, so they are bits. So in our PB model, I maybe should have said this. This is a sequence of PI variable. I just don't want to write them out. So the p bit 1, p bit 2, using the 2's complement representation. But you can think of them as integer value variables. Yeah. And just like the CP variables, we can introduce 0, 1 direct encoded variables on the fly as needed during the proof. And if I was showing you
the here is actually nice, because when you have this telescoping proof, I mean, that's actually what's going to happen with the bits. Like they're all just going to vanish into
so this actually relies on the bit
like a completely honest cutting.
And this is something that we got questions about, and we said no, we do actually need it to be bit encoded here in order to get this nice telescoping property. But that's the beauty of being able to reify and use both, because a bit later on we actually rely on them being direct encoded. So having both in the PB encoding is really great. So as I said, we're not telling you what what propagators you ought to use, just saying that whatever propagators you decide to use, we can proof log them. So one property that solvers seem to make use of when looking at their source code and seeing the various things that are written about them is that we can spot that if the all different constraint is already enforced, then the condition of there being no subcycles is exactly equivalent to saying that all the vertices are part of one cycle, which is equivalent to saying that every vertex is reachable from every other vertex, which is equivalent to saying that there is only one strongly connected component in this graph. So here, there are two strongly connected components. So if your solver had reached this state in terms of the possible values in variables domain, it should be able to contradict immediately and backtrack. And this is not something that's NP hard. There's actually a polynomial time algorithm for detecting strongly connected components due to Tarjan. And so solvers can implement that and get a lot more propagation out of it. So can we proof log this? Can we contradict on our PB encoding when there are more than one strongly connected components in the graph? And I'm very close to being at time, but that's fine because I'm not going to show you basically any of this in actual detail. Instead, I'm going to show you basically the high level of what is done in the PB proof without writing any PB constraints whatsoever. So what we can observe is if there is more than one strongly connected component in the graph, then we know that there is some vertex which cannot reach every other vertex, right? Otherwise, there would be one strongly connected component. And in fact, I'm going to tell you that by applying Tarjan, we can actually know in the solver exactly what this vertex is very easily. So in the proof, we can run an argument that collects the possible position values starting from this vertex that doesn't reach every other vertex, and eventually reach a set of variables with more value, a set of values with more variables between them. So I'll show you what this looks like. So in this case, x0 cannot reach every other vertex. We actually get stuck in this 150 component. There's no outgoing edges from there. So what we'll do is we know that P0 is 0. So I'm calling this procedure the reach too small proof procedure. If there are better name suggestions, I would love to hear them because I spent a long time trying to come up with something better. So we know that P0 is equal to 0. If we follow the edges from 0, we know that the only values that can be 1, that are one step away from 0, are 1 or 5. So we know that the set of PB variables that can equal 1 is either P1 or P5. And then if we do another step, we'll say the set of PB variables that equals 2 is either P0, P1, or P5, because all we can do is go back to 0. And we know that we're not going to reach everything. So at a certain point, we're going to run out of variables before we run out of values. Now, Kieran showed you inequalities before where we had more values than variables and showed you how to derive a contradiction from this. Is that right? Or do you have more variables than values?
I would have had more variables than values.
Yes. So I'm kind of doing the opposite way around here because I have 4 values here, 0, 1, and 2, and 3. And I have proved in PB terms, I know it doesn't look like it, but I have proved that there are only 3 variables that can have these values. And so with some adding up wizardry, I can derive contradiction from this. And that's more of an assertion than anything else at this point.
And you're hiding a step also that somewhere you assumed, without loss of generality, P0 is 0.
No. So in this case, P0 is 0. That was part of the encoding. We defined the P variables to be. You point out one of the many technical problems with this, which spent many hours of my life, which is that what if the vertex that we identify as being the one that it has too small a reach is not P0? Then we can't just start this argument from P0 equals 0, and we were kind of depending on that. So we did think about using dominance to kind of eliminate the symmetries on the P0 variables. And this is one of the things I was maybe going to ask Bart about at the end of his talk. But instead, we did something more painful, but much easier, which is, or it seems like it was much easier, which is that we introduced another set of P variables that instead have whatever vertex we want to be the start vertex as being the start vertex.
Are you doing a shadow circle?
I don't think this is quite as bad as a shadow circuit.
No, so it's purely an extension variables argument. It's just introducing a ton of extension variables. But you can think of them as the P variable shifted by a certain amount. That's the sort of way it works. And so the point being, we have this procedure. It's going to be treated as a black box procedure in the last 3 slides. That for any vertex V, we can derive contradiction if the reach of V is too small. And using that theorem that I showed you well back, where you can do anything under implications, if you can do it without implications, we can also put whatever assumptions we want on the right-hand side of this proof and prove according to those assumptions that the reach is too small. And then we realized that there's a whole bunch of other circuit propagation rules that come out of Tarjan's algorithm. And actually, all of them turn out to be pretty much this reach too small procedure in terms of what they're doing. So I told you Tarjan's algorithm, or maybe didn't tell you this. Tarjan's algorithm does a depth-first search of the graph, and it finds strongly connected components. But also what it does, just as a kind of side effect, is it identifies potential subtrees below the roots. So we do a depth-first search. We find this is everything that's below 1, and there's nothing else. And then we backtrack and we'll do a depth-first search. And we might discover multiple subtrees. And what people have noticed, and what was due to Mats Carlson's personal communication, is that it's a useful property of this graph is that if we do have multiple subtrees below the roots, then any edges between subtrees can only go from later subtrees to earlier subtrees. And you can see that because if there were any edges going the other way, they should have been part of that earlier subtree.
So can I just repeat to say, so what you're saying in particular, just from that depth first search tree, you're inferring immediately that after 0 comes 7, 9, or 8 and nothing else.
Yes, precisely.
And your solver could be smart enough to just 0 out like all other guys.
Yeah, so there's just basically a lot of incidental pruning that we can do as a result of knowing And one of the reviewers actually put it quite nicely, which is that we've essentially got a partial ordering on the vertices out of this depth first search without even fully meaning to. And this allows lots of extra pruning inferences. And the point of our paper is that we can reuse the reach too small procedure for all of these. So to start with, the prune root rule was what it's called in Peter Stuckey's paper, which is just that we can remove any edges that go to any subtrees earlier than the last one. So the first subtree that we have to visit in the Hamiltonian circuit, as Jakob just said, has to be the last one. And that's because if we visited this one first, then we'll never get back here before we visited the root twice. So we proved this essentially by contradiction using our reach too small procedure. So let's justify this x0 is 4 removal. So assume that x0 is 4. And we notice that the state of the graph would then be this. So we run our reach too small procedure on this, this one, although we could have also done it on this one, because we'll see that there's nothing else coming out of 0 now, and we're never going to reach these vertices in here. We just know this. This is a property of the depth first search graph. So we don't necessarily know how big the graph is and how many vertices they are, but we know for a fact that from 4 we cannot reach everything. So we can run that procedure. And that's going to tell us x0 equals 4 implies contradiction. So that's the justification for that. Similar rule, basically just the other way around, is that we can only have vertices going to 0 from the first visited subtree. So it's kind of the opposite direction in the Hamiltonian circuit. The first subtree you visited in the depth first search must be the last one you visit in the Hamiltonian circuit. So again, we can remove any vertices that come from the later visited subtrees and end at 0. And we can justify these removals by contradiction, because if we add these in, then all different is going to exclude any other vertices that go to 0. And so we cannot reach anything outside this subtree from this subtree. And again, that's just a property of the graph that we've just identified. So we can run reach too small from 1. Okay, one last one, and then I shall wrap up. This is the one that caused a little bit of pain. So the most general version of this rule is that we can also prune edges that skip subtrees, right? For the same reason, because once we've gone, we can never go back without visiting the root twice. So in this case, we would remove 8 to 3. And if we assume that this vertex is taken, then these vertices disappear. But in general, there might, and I didn't pick the greatest example here because there's actually no way to get to this graph. But in general, there might still be a way to get, say, there were some more vertices in here and these connected to this one. Say there were more vertices that skipped over. You might still be able to reach this. So what we do is we encode a slightly more complicated kind of assumption that will force there to be vertices that can't reach every other vertex. And then we run our reach too small procedure twice, and we get a contradiction from that. So assumption 1 will be that we see these 3 vertices in particular in this order. So 0, then 3, then 4, right? And that means that if we assume that that is something that has to be respected, then we cannot reach everything from this subtree, because we're not allowed to get, the only way out of here is to go via 0 before we see 4. And there's definitely going to be no way to get to this subtree with this one without going through 0. That's the property that we identified.
So I should read this as I see 0 before 3 and 3 before 4. Yeah. So that's the order, but there can be lots of things in between. That's what.
Yes, yeah. So this is a, I thought this might be a nice way to so the way this is actually done is, again, in the PB for a whole bunch of extension variables that tell you about the relative ordering between the variables. It gets very messy and lots of redundance rules. But basically, we create an extension variable that says you must respect this order and then stick it in the conditions of our reach too small procedure. So we show that with this order, we can't reach everything from 1. And similarly with this order, which we carefully chose, and we can't reach everything from 4. And then we look at these 2 orders that we chose, and we see that they're actually incompatible with x3 equaling x8 equaling 3, which is what we wanted to exclude. And hand wave the argument, that's because kind of 4 just keeps getting in the way. Imagine, I wanted to animate this, but honestly, I got so sick of animating at this point, I just wanted to throw in the towel. But imagine like knitting these 2 graphs together there's no way to do it and get x3 directly after 4 with nothing in between. So that is everything to say about circuit constraints. So we can assume the negation of those two things. And sorry, it should be from the negation of these two things. We can't get, in case you were trying to do that in your head, we can't get x8 equal to 3. That's maybe a bit clearer if you were staring at the previous one. Okay, so some conclusions. Lots of complex reasoning is easy, in inverted commas, to justify with VeriPB once you know how to do it. And that proofs under implications and assumptions are quite powerful. And that's why I flashed up that theorem as well. That's kind of the only sort of unifying point between all three of these. We're not restricted by the kind of a consistency enforced by CP propagators. So both smart extensional constraints enforced domain consistency. That is by no way a requirement. We can do partial consistency for circuits well. And I can also confirm the power of proof logging as a debugging tool. There are many cases where I've done incredibly stupid things in my, because I had to re-implement these propagators as part of doing this. And I would not have caught it without proof logging, simply due to the fact that the test cases are such specific instances that I was still getting the right answer out of the solver. It's just I was getting there via some kind of unsound reasoning, and exactly as Jakob said in the earlier case. And I put a few examples of this in at least one of the two papers I talked about today. So future work, there's many, as you saw the big long list scrolling, many more propagators to do. A logical thing for me to do would be to do propagators that are related to the ones that have already been done. So from regular, we can maybe do constraint regular. I made a start an MDD from circuit, there's sub-circuit and path constraints. It's also worth looking at propagators that enforce yet different kinds of consistency. So we've done some things on bounds consistency already. This is maybe a candidate for discussion at some point if anyone's interested. So I have implemented multiplication constraints, and I have about 80% of the proof logging done for that. But there is yet more technical pain to work through for that. But it's all great fun, and proof logging for CP is looking very promising. So that's the optimistic conclusion. Thank you.
So two things that I would like a question or two for Matthew, and one or two volunteers to run through the corridor and see if there's coffee outside of the door and bring it back to us in that case, and maybe some fruit also. So yeah, so any questions about your favorite CP propagator? Yeah, or other?
Maybe a silly question, but how many of the remaining propagators would you expect to go smoothly with the proof logging?
So there's a nice thing, at least about Smart Table, is that it gives you a whole bunch of other global constraints that can be efficiently represented as a Smart Table. So in terms of, so Kieran's claiming them in the list of propagators that we've done. So we can do LEPS, we can do at most one, we can do. Same with regular, you can do stretch, you can do kind of geost. So in a sense, those are done in a little bit. We also think that cumulative, so this is a scheduling constraint, should be not too hard. I mean, I guess the optimistic answer is we're thinking that this proof system is it, that we can do all of them. Like I would, but it would be an equally interesting outcome to hit like a hard roadblock that like we don't really know what this might be. But if there was a CP propagator that's genuinely doing something that's beyond what VeriPB can obviously proof log, then that would be interesting. But we're currently sitting at the point where we don't think this is going to happen. It's VeriPB is the thing.
Some of these crazy destructive scheduling algorithms, the energetic reasoning stuff, I don't think we can proof log because I don't understand what the heck we're doing.
Well, that's I mean, there's also questions about floating point numbers as well, which a lot of constraints do deal with. But there have also been thoughts about this in VeriPB as well. But yeah.
You said you're 80% done with the multiplication constraint. How linear is it to do 80% of work? Like for me, it's often that the last 20% take more time than the first 80%.
Yeah, I'd like to say so. I mean, I got a lot of it done and then was doing reviews for the circuit paper this next week. So I need to go back to it, but we're at a certain point now where I know on paper how to do it, and I could like claim on a board that we know how to do it. It's the actual implementation details and me feeling like I need to become a better C++ programmer. So I'm hoping 80%, this is a linear, I'm hoping this is a linear scale and that it really is only like a couple weeks at most.
But it was so in the past for the other things you did the prooflogging for that.
So yeah, no. Some parts just went very, very quickly. Like it was unbelievable that, oh yeah, this is really easy. And then you hit one snag and then you're 6 weeks in. I mean, anyone that's doing a PhD right now will know this is the way.
Well, yeah, so multiplication will be done for triple AI. Maybe.
Yeah, well, Kieran said
Next year.
let's do a circuit so we can go to Uppsala and CPIR.
Good, so let's thank Matthew again.